Hi everyone, and welcome to another video of this channel. So in this video, we will be finding an explicit formula, a closed form for the Fibonacci sequence. So the Fibonacci sequence has 0th term equal to 0, first term equal to 1, and then each term is the sum of the previous two terms. And this sequence is really widely used. It's kind of one of the more basic recursive sequences that shows up in nature a lot too. So it's not just purely mathematical. But what if we want to find the 100th term of the Fibonacci sequence? In order to do that, we have to find the 99th and 98th term, for which we need to find the 97th and 96th term, and so on and so on and so on. So that's like 100 terms we need to calculate. But what if we just had this formula where you plug in n, and the formula spits out the nth term of the Fibonacci sequence? So that would be an explicit formula, a closed form of the Fibonacci sequence. And so in this video, we will be finding this closed form using linear algebra. And one more comment before we move on, this method that I use right here, it can be applied to any linear recursion. So any formula where one term is expressed in terms of a previous term, you can, so if you want to find an explicit formula for the sequence, you can use this method. So to start, suppose we have this vector right here, which has entries of also the n plus first term of the Fibonacci sequence and the nth term of the Fibonacci sequence. Let's call this the n plus first Fibonacci vector. And so we ask the question, how do you go from the nth Fibonacci vector to the n plus first Fibonacci vector? In other words, what linear transformation must the nth Fibonacci vector undergo to transform into the n plus first Fibonacci vector? And the answer is 1, 1, 1, 0. So this matrix right here. Why? Well, because this 1 multiplied by f of n plus this 1 multiplied by the fn minus 1, right? This just matrix vector multiplication is equal to this term right here. And then 1 times fn plus 0 times fn minus 1 is equal to fn. But now to go from the n minus first Fibonacci vector to the n plus first Fibonacci vector, we need to do this transformation 2 times, so it's squared. And we just continue this pattern from here. And we notice that to go from the first Fibonacci vector to the n plus first Fibonacci vector, we have to do this transformation n times. But then also notice that the first Fibonacci vector is the vector 1, 0, right? That's just by this right here. And so we expressed this n plus first Fibonacci vector in terms of this linear transformation to the nth power times this vector right here. And so now let's just look at our inspiration. So notice that this matrix to the nth power has no closed form. So what do I mean by this? I mean that there is no matrix that has an n in its entries, either in the exponent or elsewhere, such that when you plug in n, you get this matrix to the n. So that's what I mean when I say that this matrix has no closed form. And it is quite hard to calculate. Even for n equals like 20, it's still quite difficult, even for the calculator. But notice that there are certain matrices that have closed forms. In other words, for these matrices, there are other matrices that have n in their entries, such as when you plug in n, you get the original matrix to the nth power. So these are diagonal matrices, right? So these are the matrices A0, 0B, right? They have 0 everywhere except for on the diagonal entries. And if you raise them to the nth power, you in fact get A to the n, 0, 0, B to the n. So this is what I mean when I say the n is in the entries. And so now our goal is to try to make this matrix of the form of some matrix times a diagonal matrix times some other matrix. Maybe that will be more convenient. So you want to diagonalize 1, 1, 1, 0. So now I'm going to show like how we diagonalize matrices. So let's suppose we have a non-singular linear transformation A, and we want to diagonalize it. So what do? So we write it in the form of Q lambda Q inverse. So Q is what we call a change of basis matrix. Lambda is a diagonal matrix. And then Q inverse is the inverse of the change of basis matrix. So now, of course, we don't know how to calculate these guys yet, but ideally, what we can do with this is, so let's suppose we want to raise this matrix to the nth power, right? We want to find a to the n. Well, this is just Q lambda Q inverse multiplied by itself n times. Now notice that all the Q inverses and Q's, right, by the associativity of matrix multiplication, get cancelled out. So all the Q's and Q inverses on the inside get cancelled out, and now there are n lambdas, right? They're multiplied by each other. And so we have that this right here is Q lambda to the n Q to Q inverse. So in fact, just raising this matrix to the n, all it does is raise this matrix to the nth power. And so this is ideally what we want to find, right? Because these guys right here, they do have a closed form. But how do we calculate Q lambda and Q inverse? How do we calculate the entries? Well, now we're just going to go through the concept of change of basis. So what if we have arbitrary matrices, A, Q, and lambda, right? So A is once again a linear transformation, but in our basis vector system. So this is like our normal linear transformation in I hat, J hat. So once again, I mentioned that this whole process works for general recursions when like for instance, there are 3 terms being added together in the Fibonacci sequence. We can have like I hat, J hat, K hat, for instance. And then the Q inverse is a change of basis matrix. It changes from our basis vectors to different basis vectors. And let's call these guys like just any vectors. So v1, v2, right? And these v1, v2, these are the columns of Q. And then lambda is a linear transformation, but in our new basis vector system. And then Q changes back to our old basis vector system. So in other words, we first change to a new set of basis vectors, do our transformation in that set of basis vectors, and then change back to our old set of basis vectors. Now, what happens when lambda is diagonal, right? So this is for arbitrary matrices. What if lambda is diagonal? Well, notice that what do diagonal matrices do, right? They scale, right? So so lambda once again is a linear transformation in our new basis vector system. So in fact, lambda scales v1 by lambda 1, so that's the first diagonal entry, and v2 by lambda 2. And this is once again for the 2D case. So we can have like n lambdas and n v's, for instance, if our recursion has n terms. Okay. But then this right here, so the scaling of these new basis vectors, this directly corresponds with the fact that in general we're scaling these new basis vectors by our original matrix A. So applying A to these basis vectors is the same thing as scaling them by lambda 1, lambda 2. This is if this middle matrix right here is diagonal. And so if this matrix is diagonal, we have that A times any of these new basis vectors is equal to the diagonal entry times its corresponding new basis vector. And so this is the connection between this right here and this right here. So this being diagonal and this. And so now we can solve this equation right here. So first we make this side right here look more like matrices. So we add this identity matrix right here, and then we can subtract lambda iv to the left hand side, and we can factor out the v, and so this is equal to 0. So now we have 2 cases. The first case is when this vector itself, this v, is the 0 vector. But this case is trivial. We won't consider it. And then the other case is, well, the only way that a matrix times a non-zero vector can be equal to 0 is if that matrix is singular. So its determinant is equal to 0. And so this is, in fact, the non-trivial case of this equation. So this, in mathematics, it has a special name. This is called the characteristic polynomial of the matrix, the linear transformation A. It's a polynomial in lambda, right? So this matrix A minus lambda I, it's just A, but with lambda subtracted down its main diagonal. And so this right here, if we know the entries of A, is a polynomial in lambda. And so in order to get the lambdas, right, the diagonal entries of our big capital lambda matrix, we solve the characteristic polynomial. And these lambdas right here, they have a special name. These are called eigenvalues. And then we substitute these eigenvalues into the equation, right, the original equation, AV equals lambda V. Just like this. And we get our eigenvectors. These are the VI, right? All the new basis vectors. They're called eigenvectors. And then once we do that, we just use the lambdas and the V's to diagonalize A. So that was a brief recap of diagonalization. Now we will diagonalize the Fibonacci transformation matrix 1110. So our first step is to find the eigenvectors and eigenvalues. Right? So first we say, okay, the determinant of A minus lambda I is equal to 0, and the determinant of A minus lambda I is this right here. And then after just evaluating the 2 by 2 determinant, we get that this is equal to lambda squared minus lambda minus 1. And notice that we want this to be equal to 0. And so we get that our first solution to this equation, right, our first eigenvalue is phi, the golden ratio. This is equal to 1 plus the square root of 5 over 2. Our second one, right here, is psi. This is equal to negative 1 over phi, or 1 minus phi, actually. It's also equal to that. And this is equal to 1 minus the square root of 5 all over 2. And so we have these two eigenvalues, phi and psi. And so now, once again, we plug these eigenvalues into AV equals lambda V to get the eigenvectors, just like this. So we have that A, 1, 1, 1, 0 times the first vector, right, x1, y1, is equal to phi, this is the first eigenvalue, times the first eigenvector. And so after that, we get this system of equations, which after solving, we get that v1 is equal to phi 1. So that's the first eigenvector. And then very similarly, we do the same exact operation on the second eigenvector and eigenvalue. And we get that v2 right here, the second eigenvector, is equal to psi 1 right here. And so now we use this information to diagonalize A. So remember, A equals Q lambda Q in inverse, right? Q's are the change of basis matrix, and A is the diagonal matrix. So remember, Q has these new basis vectors as its column entries. Lambda has the eigenvalues as its diagonal entries. And then Q inverse is just like this. So now remember, when we want A to the n, that just raises lambda to the n. So we have this right here. And now, finding the inverse and doing matrix multiplication, we get that A to the n is equal to 1 over the square root of 5 times phi to the n plus 1 minus psi to the n plus 1. And then the second entry is 1 over the square root of 5 phi to the n minus psi to the n. Similarly for this entry right here, and then this entry right here looks also similarly. And so now we go back to this right here. So in fact, this right here is our closed form for A to the power of n. This right here is the closed form. So we just diagonalized it. And so now we can just plug this into this part right here. So the n plus first Fibonacci vector is equal to our Fibonacci transformation matrix to the n times 1, 0, which is equal to this new matrix times 1, 0, and this is equal to this thing right here. Just like this. And so now we can just compare these two entries. We can compare the top one or the bottom one, any one we choose. We get the same result, that the nth term of the Fibonacci sequence is 1 over the square root of 5 times phi to the n minus psi to the n, where phi and psi are the golden ratio and negative 1 over its reciprocal. So I find that this is in fact truly amazing, because we have just found an explicit formula for the Fibonacci sequence. Now, if we want to find the 100th term, we can plug in 100 for n, and we get the Fibonacci, the 100th term. So this formula is called Binet's formula. And actually, as a quick note, notice that psi is approximately negative 0.618, right? So its absolute value is less than 1, which means that as n gets really large, even for like 20, this is already true. Psi to the n approaches 0. And so in general, this term right here becomes negligible for increasingly large n. And so, in fact, we can have that the nth term of the Fibonacci sequence is approximately equal to 1 over the square root of 5 times the golden ratio to the nth power. So, if we ignore this term, which we can do for very large n, we get this right here. So, it's just another way that the golden ratio is deeply intertwined with the Fibonacci sequence. So, I hope you liked this video. Thanks for watching, and I'll see you next time.